Welcome to this webinar. My name is James Pond and I'm CTO of Lumerical, and I'm going to tell you a little bit about our 2013B release. So first of all, I want to go through a quick review of our products and then tell you about this 2013B release, go over some of the new features, and then go through a few featured applications. So in terms of Lumerical's products, we have four products. The first is FDTD Solutions, which is a 2D and 3D Maxwell solver, which allows you to solve for optical properties of wavelength scale structures with arbitrary geometries and arbitrary material properties. Mode Solutions is a waveguide design environment which allows you to find the properties of waveguide modes and fiber modes, as well as including an omnidirectional propagator for in-plane propagation, which allows you to solve problems very quickly like this ring resonator. Device is a 2D and 3D finite element Poisson and drift diffusion solver, which allows you to solve for the electrical properties of devices, and we typically use it for optoelectronic devices in conjunction with FDTD solutions and mode solutions. And then INTERCONNECT is our photonic integrated circuit simulator, which allows you to simulate large-scale photonic circuits at a higher level of abstraction in a way that's more similar to SPICE modeling in electronics. In terms of product performance, since we began in 2003, our products have become very well known and well cited. And in this graph you can see the number of references to our products in publications, patents, and presentations each year. And in 2012 alone, there were more than 500 references to Lumerical products. Now I'm going to talk a little bit about Release 2013B. What this is a synchronized release of all of our products. So in terms of the specific product versions, it's FDTD Solutions 8.6, Mode Solutions 6.5, Device 3.0, and INTERCONNECT 3.0. And the reason we're releasing all the products together is that it allows us to get all the latest features to our customers as quickly as possible. And also it enhances the interoperability of our products, which is very important as we look at modern components, which often involve electrical as well as optical behavior, or where components need to be modeled first with device level solvers and then parameters extracted for use in more and larger scale simulations, such as can be done with INTERCONNECT. So in terms of new features in this release, for device, it's a major change. There's now a 3D multi-threaded finite element solver to complement the existing 2D finite element electrical solver that was there before. So this allows us to take very complex three-dimensional geometries and solve for the electrical properties. And I'm going to show you an example in the application section on CMOS image sensors where this is extremely useful. INTERCONNECT, we're looking towards an EDA-style design flow that can be used for photonic circuit simulation. And so we have optical SPICE netlist import as a feature, as well as a file transfer method that supports Agilent, ADS, and Mentor Graphics ELDO time domain waveform formats. And in addition, we have enhanced support for the development of process design kits, which is essential for any EDA flow. And of course an expanded element library, which includes an increasing number of elements, particularly ones that help us to simulate electrical portions of mixed signal circuits, where the signals involve both electrical and optical signals. Now in terms of the direction that we're going with this, what we see is a unified EDA flow for photonic circuit design that fits into the context of a larger EDA flow for electronic circuit design. And so we're collaborating with Mentor Graphics, OPSIS, and other parties. And the goal is this unified electronic design automation and photonic flow with associated process design kits. And INTERCONNECT 3.0 is really a first step towards achieving this goal. So for more information on this, I'd invite you to take a look at our Photonic Integrated Circuits week of webinars that's coming up in a couple of weeks. Please see our website for details, and particularly the first day is very interesting. We've also given an invited talk at Photonics North June 3rd through 5th next month. There's also a number of ongoing OPSIS workshops, and I'd invite you to take a look at the OPSIS website for that. And recently, Mentor Graphics released a press release that discusses this collaboration and the vision for where we're going. Now, just to give you a quick idea of how this can work, the idea is that you can lay out extremely complex photonic circuits using a tool like Mentor Graphics Pyxis. And this is an example of a portion of an 8-channel WDM transceiver. Now, once you've laid this out with Mentor Graphics Pyxis, you get all of the excellent features that come with an electronic EDA design flow. So you can do design rule checking, layout versus schematic, and that type of thing. And in addition to that, you can now use the Optical Spice netlist import to be able to take the circuit or a portion of the circuit and import it directly into INTERCONNECT to be used as a test bench for circuit verification and simulation. And so the nice thing about this is that you're able to verify that the circuit that you've actually laid out and are going to be sending to the foundry to be manufactured is actually functions the way that you intended. And of course, in order to be able to do the simulation, we need a PDK within Interconnect that has all of the different components that are supported or can be manufactured at a particular foundry. And that's where the idea of enhancing the ability to develop these PDKs comes in. And I should also say that we're working closely with OPSIS to develop an extensive set of components for their OPSIS IME PDK. In terms of other new features, Mode Solutions now supports nonlinear and gain waveguide modeling. This allows us to simulate soliton propagation, 4-wave mixing, gain and lasing, modulated refractive index, and so on in waveguide systems. And the nice thing about doing this in Mode Solutions, which is a very, very fast propagator in the time domain, is that it allows us to simulate very large-scale waveguide systems, as well as to simulate for long enough to see some of the nonlinear effects, which often require much longer simulations than when we have purely linear materials. So I would invite you to take a look at an upcoming webinar on nonlinear and gain simulation in waveguide systems, and you can learn about all of the details of this type of simulation. Another feature that comes through all the products is improved data visualization. So it may not seem like a large thing, but it's quite important in terms of the 1D data visualization that we've done a lot of nice improvements. So we have a much better support for zooming and panning and scrolling, and nice features like better log plots and log plots and so on. In addition to that, we've added a vector plot capability. So this allows us to, for example, take a look at the pointing vector coming out of FDTD simulations. What I'm showing here is a simulation of a bullseye plasmonic device on the left-hand side, and on the right-hand side we can see on the transmission side the pointing vector on the transmission side of this device. In addition to that, we've added the ability for very easy export to ParaView. Now, ParaView is an open source 3D visualization software which allows for very, very sophisticated three-dimensional visualization of data sets. And so it's quite easy to create the types of images that you see here. And it's really nice to be able to work with ParaView, and we hope that our customers will as well, and give us some feedback on the different types of visualizations that they'd like to see supported, because once we see some useful types of visualizations, we can then integrate more and more of those directly into our own visualization framework. In addition to the major features, there's also a wide range of small features and improvements. For example, in terms of our analysis, we now have multi-threaded FFTs, linear algebra, and near to far field projections, so that can speed up a lot of the analysis and post-processing of results that's done on your computer. We also have made some major improvements to the scripting language, so we have support for new data types such as cell arrays, structures, and unstructured grid data sets. We've also added support for FlexNet licensing, and we've improved the MATLAB file I/O, and so we now have the capability to not only write MATLAB files but also read them directly in our scripting language. And of course, there's many more of these types of small features, so I'd certainly encourage everyone to upgrade from their existing version to the latest versions of the software. Now I'm going to go through quickly a few featured applications, and more information on each of these applications can be found on our website or in upcoming webinars. So these are CMOS image sensors, electro-optical modulators, solar cells, and an 8-channel WDM transceiver. So in terms of CMOS image sensors, this is something that we've been simulating for a long time. And the way we work is we typically start with the optical simulation, and the question that we're trying to answer is how many photons do we absorb and where are they absorbed in the device? And this question is answered with FDTD solutions. And once we know that, we can actually generate or create a generation rate from the FDTD results, which is telling us how many electrons we're creating per unit time and where they are in space. And so we'll get a three-dimensional map out, and this is a cross-section through that map. And then from there we import that data into the electrical simulation, because it's a term that comes into the drift diffusion equations. And then we do now a three-dimensional simulation with device, and we can figure out how many electrons do we actually collect. And of course there's some nice features that exist in all of our software, such as the import from GDSII format. So we can take these incredibly complex structures, read them into our software, and then as you can see in this screenshot, we have a nice three-dimensional representation of a very sophisticated three-dimensional geometry. We can then run the electrical simulation. So what you see on the left is a cross-section of the device simulation, and on the right-hand side is actually the three-dimensional generation rate that was imported from FDTD solutions into device. And this allows us to do calculations such as the transient response with varying input power. So we can start out looking at time 0, where we open the shutter, turn on the illumination. We then collect electrons for a certain amount of time, turn off the illumination. We have a charge transfer step, and then a sample output. And so from this we can look at a variety of characteristics of the device, and for example we notice that if we have illumination which is too large, then we've simply oversaturated the device. So for more details on this, I do encourage you to see a recent webinar video that's available on our website, and it gives you many more details about the simulation of CMOS image sensors using our software. Another application is a traveling wave modulator, and so this is a device where we create a waveguide and then apply a voltage across the waveguide, and we're able to change the electron hole density throughout the waveguide, and by doing so we change the refractive index, make a very small change in the refractive index, but this allows us to make a Mach-Zehnder modulator. So here we would calculate the electron hole density, which you can see in the image on the left-hand side with device. And in the process of doing this, we can also calculate quantities like the capacitance of the device. And what you see in the lower curve here is actually the comparison between the calculation of device and the measurement in a published result. And once we have the electron hole density throughout the device, we can then import that data into mode solutions and convert it into a change in refractive index in the waveguide, and we can then calculate the effective index of the waveguide as a function of applied voltage. When we know the effective index as a function of applied voltage, we can then import that information into interconnect, and we can include or simulate the response of this traveling wave Mach-Zehnder modulator, and we can also include that Mach-Zehnder modulator then in larger scale circuits and systems. Another type of interesting modulator is a three-dimensional interleaved PN junction microring modulator. And so here we actually have this interleaving, which requires a three-dimensional simulation with device. And again, we can calculate the electron hole density throughout the device as well as the capacitance of the device. And once we know the electron and hole density changes now as a function of three-dimensional space, we can import that information into FDTD solutions and use that to calculate the change in optical properties of the light as it travels through a waveguide made out of this interleaved modulator. And therefore we can look at the V-pi as a function of applied voltage, and we can also consider what is very important, which is the change in loss as a function of applied voltage. Another application is solar cells. Now with solar cells, very similar to CMOS image sensors, we start with the optical modeling. So this is a grating based device which is designed to try and reduce the reflections and enhance the absorption of light to higher efficiency solar cells. So we would simulate 1 unit cell of this with FDTD solutions, and from that simulation we can extract the generation rate, which is the number of electrons and holes per unit time as a function of space that are created under solar illumination. We can then take that information and import it into device. And of course, device is now working on a finite element mesh. We can calculate the relevant electrical characteristics, and we can then calculate things like the current density and the power versus voltage and determine the maximum power point. And so by doing this combined optical and electrical modeling, we're actually able to do an end-to-end simulation from photons to electrons and calculate the true power conversion efficiency of these devices. And finally, the last featured application is an 8-channel WDM interconnect transceiver using ring modulators. And this is simulated with interconnect, and as you can see, this design uses so many components and so many ring modulators that it would be unrealistic to try and simulate this entire device with something like FDTD solutions or mode solutions. Also this device includes components which have both optical and electrical characteristics. So of course the modulation is driven electrically, but then the signal is carried optically through the device. Now in terms of results, we have a spectrum analyzer which is at the output of the multiplexer, and there we can see the 8 modulated channels which are present. We can use oscilloscopes at different positions, and this one is placed at the receiver side, so we're looking at the bit stream after we've gone through the transmitter and into the receiver. And then we have eye diagram calculators which allow us to look at the received signal and measure quantities such as the bit error rate or the Q factor. So I've come to the end of this presentation on release 2013B. If you'd like more information, I'd invite you to see the product pages on our website as well as the knowledge base on our website, which has a lot of information and detail about these new features. I'd also ask you to connect with us on LinkedIn, and you can get access to all kinds of information and about our products, services, and upcoming webinars. And of course, you can always email us if you have some other questions about the new release that you would like answered. So thank you very much for your interest.